Hello, I'm Tyler, and we'll be going through a recommended problem from Chapter 5, Problem 23 from the book. So the original problem, we were given a roller A and a pin at B can both support a load of 4 kilonewtons and 8 kilonewtons respectively. We're asked to determine the maximum intensity of the distributed load W measured in kilonewton meters, kilonewton per meter, so that failure of the supports does not occur. So our modified problem, we've changed the angle, we've changed the distance from A to the bend here. We've also changed B to the bend here. We've changed the units from meters to feet and newtons to kips. We've changed the size of the distributed load. So here are our givens. We were given the distances, the maximum forces, and the types of supports. And here we have our free body diagram. And we went ahead and added the horizontal distance and the vertical distance using the angle here. So what's required? We're asked to find the supporting loads at each joint. And we're asked to define a distributed load, which means we need to know how to calculate that. And we're asked to solve this backwards from what we're used to. So here's our updated free body diagram. We've added the supports. We have A acting at the roller and BY and BX acting at B. BX is acting in the positive X direction and BY is positive. We can break A up into its component parts. So it has an AX and an AY component, and that'll be easier when we're solving for equilibrium. Our assumptions, we have the rectangular formula and the X bar, the distance that the resultant force will act. We found this in our formula sheet. We're also given the roller joint and the pin joint. And for a roller, it's just going to be a force perpendicular to the point of contact. And for a pin, it's going to be the y and x components, or it's going to be a resultant F with an angle. We're assuming it's perfectly rigid, it's not going to bend. It's in static equilibrium, which means we can use our three equations. The sum of the forces in the x direction is 0, the sum of the forces in the y is 0, and the sum of the moments at any point is 0. So how do we go about solving for this? My method, and you can do this any way you want, I went ahead and converted the unknown W into a resultant force because I'm more comfortable working with that. And there we use the formula for the rectangle from the previous slide. And we get that the orange F sub W is equal to pink W times 4 feet. And here we put that in a new free body diagram. And notice that the total distance of W has been converted into the resultant force, and it's acting 2 feet more from B, and a total of 2 feet from the bend here. So it's been halved, which we got from our formula in the last slide. So moving forward, we have our equilibrium equations. We can really solve it any way we want. I'm going to solve it with the moments because we're isolating one unknown usually. So we're going to sum it around B because there's two unknowns there, and we're solving for A. A has two components that are unknown, but we can easily find those using the angle. So just what I said, I mean, we have AX and AY, and both can be represented as A using some trigonometry. So the sum of the forces in B, we have FW acting 5 feet away from B, causing a counterclockwise motion, which is positive. We have AX 3 feet above B, causing a clockwise motion, so it's negative. We have AY acting 11 feet away from B, also causing a clockwise motion. So we're going to solve for FW, and we have AX and AY. That's not really helpful. We're going to try to get that into our one variable, so A. So we're just going to substitute in with our trig identities here. And then we multiply the 3 feet and the 11 feet by the trig, the cosine of the angle and the sine of the angle. And we're going to divide by 5 feet to isolate FW. The feet are going to cancel, and we end up with FW is equal to 2.12A. So, we're not done yet. Now we can use the FX and FY. It doesn't really matter which one. I'm going to do FX because there's only two forces. We have positive AX and positive BX. And I should have noted that it's positive here, so that the A, the support force at A is acting in the correct direction. We've drawn it correctly. So here we have, and that's going to be more clear why I said that, because when we're solving for BX, we have a negative here. And that means that the way we've drawn it is in the opposite direction, which is actually acting. So we have BX is equal to, and I've substituted AX for in terms of A. So we have BX is equal to negative A sine of the angle. Now that doesn't really help us very much. I mean, two unknowns, we're not trying to, we don't know what to do with that. So we're going to use a little strategy here, and that's why we solve for the moments about point B. So we know A. We know A is FW divided by 2.12. That's just rearranging this equation over here. So we're going to plug that in. We're going to plug this into A. Now we have BX is equal to the negative FW divided by 2.12 times sine of the angle. Doing some algebra, we find that FW is equal to negative 0.283. And again, the negative just means that it's acting in the incorrect direction as drawn. Okay, so that was really good of us to do that, because now we have BX in terms of FW, which is what we're trying to find. So now we have our last equilibrium equation. So we have FW acting negative in the negative y direction. We have both AY and BY acting positive. We're solving for BY, so we just rearrange our equation here, and we substitute AY for A times the cosine of the angle. And again, we're going to do that little trick we did last time. Using this equation here, A is equal to FW divided by 2.12. And then we're just going to multiply that by cosine of the angle. And then we just do basic algebra to find that BY is equal to 0.623 FW. And it's positive, so we know that we've drawn it correctly in the diagram. So I want to make a note that in the problem that it asked us, it told us that B could only possibly support 21 kips. 21 kips total, meaning resultant, the magnitude. And here we have BX and BY, which are components of a resultant force. So we're going to find the magnitude of BX and BY, or of B, because the total supporting force is 21 kips. That's not just in the Y direction, that's total. The pin can only support 21 kips. So we solve for the magnitude, plugging in from the equations that we found. We have B is equal to 0.684 of FW. We rearrange that to find FW in terms of B. And now we have FW is equal to A and FW is equal to some B. Okay, so we go back to our question here. We see that A can only possibly support 9 kips, and B can only possibly support 21 kips. So we have, it can be less than, it just cannot be greater than. And we know that FW is equal to 2.12A. So if A was at its maximum, it would be 9 kips, and we find that FW would be the maximum 19.08 kips. All right, and we need to do that for B just to check. And if we plug in B's 21 kips, that's going to be 30. So FW is much larger if we do the maximum of B, which means the maximum value FW can possibly be is this 19.08 kips. And that's because if it was any greater, A would fail. The supporting force would be greater than 9 kips and A would fail. So here we're going to go back to the distributed load because that's what the question calls. So we have our equation that we remembered. FW is equal to the distributed load times 4 feet. We have FW here. And we divide that by 4 feet. So W is equal to 4.77 kips per foot. And that's our answer here. So that's what the question asks for. That's what we found. And now just to summarize, in conclusion, is this a reasonable value? And I believe it is. If we checked our work and worked forwards this time using the distributed force, we would find that A, the supporting force at A is less than 9 kips, and B, it would be less than 21 kips. So both supports would be structurally sound. And so how did we get to this answer? Well, we worked backwards. We didn't know the forces, and we calculated W in terms of the support reactions. Then we compared the support reactions to each other using the maximum supporting loads that would remain structurally sound. And then we chose the force that was most reasonable. And we were careful about signs, knowing which directions the support reactions were in comparison to the drawing. And we were careful using trig, determining the components of our support reactions at A. And that's it. If you have any comments or suggestions on how I can make this better, please let me know. With that said, thank you for watching, and I'll see you next time.